A user asks a question about the 2024 Q3 earnings report. Your vector database has documents from every quarter across 5 years. Semantic search will scan all of them. Most of those documents are completely irrelevant before the search even starts. Metadata filtering lets you tell the database to only search documents where year equals 2024 and quarter equals Q3. That scopes a 5-year corpus down to a single quarter before a single embedding comparison is made. At small scale, metadata filtering is a nice to have. At 1 million documents, it is essential. Without it, every query compares the query embedding against every stored vector. With a well-designed metadata schema, you can eliminate 90 to 99% of the corpus before semantic search runs. This makes retrieval faster, cheaper, and more precise because the model is no longer distracted by documents from completely unrelated categories. The metadata you can filter on is only as useful as the metadata you stored at index time. The most valuable fields to capture are source file name, page number, creation, or publication date, a category or department label, language for multilingual systems, and version number when you keep historical versions of documents. The rule is simple. Any dimension a user might naturally want to scope their search by should be stored as a metadata field when the chunk is indexed. Metadata is added at index time as a dictionary alongside each document. We store source file name, year, quarter, and category for each chunk. Every chunk from the same source document gets the same metadata values. This is important. The metadata does not describe the chunk content. It describes the document the chunk came from. When a user filters by year 2024, they get all chunks from 2024 documents, regardless of what those chunks say. A simple where filter is a dictionary pass to the query method. We use the $EQ operator to match documents where category equals finance. Chroma evaluates this filter before running the similarity search. Only chunks tagged with finance category are compared against the query embedding. The rest of the corpus is never touched. Chroma supports $EQ for equality, $NE for not equal, $GT, and $LT for numeric comparisons, and $IN for matching a list of values. Compound filters combine multiple conditions using $AND or $OR at the top level. Here, we require both category equals finance and year equals 2024. Only chunks that satisfy both conditions enter the semantic search. You can nest $AND and $OR to build arbitrarily complex filter logic. A $OR might be used to search across 2 departments at once, or across 2 years when a query spans a reporting boundary. Dynamic filter extraction uses the language model to parse filter values directly from the user query. We write a prompt that asks for category and year to be extracted as JSON. We instruct it to return null for fields not mentioned in the query. Temperature 0 ensures deterministic output every time. This prompt is the first step in a 2-step process. The second step converts the extracted values into a Chroma where filter. The build filter function calls the language model, parses the JSON response, and constructs a Chroma where filter from whatever fields were extracted. If only one condition was found, it returns it directly. If 2 or more conditions were found, it wraps them in a $AND. If no filter values were found, it returns an empty dictionary, which Chroma treats as no filter, meaning the full corpus is searched. This graceful fallback means the function is safe to call on any query, regardless of whether it mentions metadata. The full pipeline calls build filter first to extract any metadata conditions from the question. It then passes the where filter directly to the Chroma query. If no filter was extracted, the where parameter is none, and the full corpus is searched as normal. The rest of the pipeline is unchanged. The language model receives context that has been scoped to exactly the right subset of documents before semantic search even touched them. You now know how to store rich metadata at index time, apply simple and compound filters in Chroma, and extract filter values dynamically from user queries using a language model. This is the last retrieval optimization episode in the series. In the next episode, we move into production. We take everything we have built and serve it through a FastAPI endpoint with streaming responses. Subscribe so you do not miss it. See you in the next one.